Hi, this is Jack Nilsson again. You may have viewed some of my other videos. Since those videos were posted on YouTube, there have been a number of conversations. I've been contacted by individuals in the industry and radio operators. There's been additional forum postings, and after having some of these conversations, it has been requested that I put together yet another video, a video that encompasses some of the matter of the discussions that have been had that deal with the science additionally. So there are a few interesting things. For example, some of the discussions that are had, some of the dialogue or the communication on the forums were really very, very good. There are some that have talked about knowing me years ago, and based on their kind expression of my attributes, said, if Dr. Nilsson, if Jack Nilsson develops it, it's good. And I thank you for that. And that happens sometimes. You know, we look historically at scientists, physicists, inventors, and we see some similar things that occur. Sometimes just character traits alone are all that's needed for somebody to give support, and that's wonderful. But often that's not the case. Sometimes when things are developed, new concepts, instead, sometimes there are a few that embrace it, and this has been history for me as well, while many don't. Then, after some time, there may then be supportive evidence from other experimenters, research people, laboratory people, whatnot, and the concept is further embraced. And that, in fact, is the case here, as I'm going to be talking more about the COMPACtenna, newer patent. So, sometimes one would hope that after developing a new concept, a new science with technology from that science, that when yet another new concept is developed by the same individual, that would be embraced automatically. But that often doesn't happen either. And so that's kind of the case here. So what I'm going to do here is talk a little bit more about the history of invention from others, and then I'm going to do what was desired, and that is to explain with additional references to other developed technologies that are in support of the kind of concepts that I had in a visionary way. One example historically, and there are many, involves the work of Ludwig Boltzmann. Ludwig Boltzmann was a physicist in Vienna, Austria, and the focus in Vienna in science and art was for order, perfect order. Ludwig Boltzmann, among others, about that time period, shortly thereafter, started talking about the science of disorder. Even years after that, with Niels Bohr and Heisenberg, the uncertainty principle. Shortly after Boltzmann's suicide, Einstein supported entirely Boltzmann's concept of the atom. So, what I'm going to do now that introduction has been said is to talk about, again, the science and technology of the COMPACtenna with references to other developed technologies, separately developed technologies in support of it that have occurred over the last 20 years. References have been made, and I'll explain the terminology to things such as on the data sheet. Superior science performance with vehicle location changes in movement. Superior science performance in non-line of sight, obstructed environments. We even look at the gain, and I smile. We'll talk about that. I'll talk about that in detail. The gain nominal, 3 plus dBi, dB over isotrope. I've seen some good discussions about dBi, dBr, dB reference, dBd, dB dipole, all these kind of things. But as it says here, in brackets, performance is greater than predicted based on gain alone in non-line of sight, NLOS, environments, which is the world we live in. So what does all that mean? No, it's not snake oil. It's true science. About 20 years ago, when I was talking about the science of radio waves in the obstructed world that we live in, with reflections, refractions, scattering, and whatnot, and before the term spatial diversity was even developed, created, coined by other developers, I was talking about capture of signal three-dimensionally in space. And it was more challenging then because these other technologies, working more not with antennas, single-feed antennas, but with electronics, with the receivers, with the transmitters, receive diversity, full diversity, transmit receive diversity, MIMO, multiple in, multiple out, and the various types. None of this had been developed yet, so it wasn't something I could reference. There were anechoic chambers for testing antennas, but the newer, such as developed by Lindgren out of Sweden and then Texas with the reverberating chamber, had not yet been developed. I anticipated back then that would occur over time, and I'll explain that a little bit more later. But so let's talk about this science. Okay, when we talk about radio communication, when we talk about something that's line of sight, yes, gain is everything, pretty much. There's atmosphere and whatnot, but just for a moment, in space, gain is everything. You want better signal, you want better throughput, you want better analog communication, digital communication, gain is the focus. I'm not discrediting that, but that's not what occurs. 99+% of the time we're communicating here on Earth. And there are other examples, but for now we'll talk about that. So, if we're talking about communication from mountaintop to mountaintop, and again, we're just thinking in terms of free space here, non-atmospheric disturbances and whatnot, although they're very real, but just for a moment so that we can get this gain thing out of the way. Gain is everything, whether it's analog or digital communication. If you want to communicate to the next mountain top, point to point, whatnot, gain is where it's at. Increase in transmission power gain or antenna gain. Tower to tower, similar kind of a thing. But when we're in the real world of communication, there are all kinds of obstruction. So in the real world of communications, we have all kinds of structures. We have man-made structures, and we have natural structures. We have trees, we have hills, mountains, we have buildings, this kind of thing. We have between buildings, we have from outside to inside buildings, from inside to inside buildings with walls and obstructions. We have all kinds of signals bouncing around, diffracting, refracting, all of these kind of things that are occurring. So when we are communicating from one point to another point, see if there's even room for us in all these obstructions, to another point in here, say we're in a vehicle, and we want to increase the reliability of communication, the power is in the diversity. And I've talked about this before. The power is in the diversity. There is a term 95% reliability in communication. This particularly applies to emergency type communications, one form of government or another, for example, where it's so important to reach that 95%, so that it's a quality communication. And it applies in both their analog and their digital radios. So certainly, if you're in a particular instance, even on Earth here, and you want to communicate more effectively, there are instances where increasing the gain, for example, of the antenna, for example, on the tower or on the vehicle itself, is going to help you, yes, in certain instances, particularly if that vehicle happens to be, again, up here on the mountain, or if you're behind perhaps some trees, and that increased gain is going to give you just a little bit more, and it's going to give you that discernible communication. Yes, that can occur. That can occur. But that is not what is occurring most of the time, that you're having drop off in your communications. Instead, what is happening most of the time that disrupts this potential for 95% reliability are very significant drop-offs in the signal strength. Slow and fast drop-offs in the environment. So a few extra dB gain of the antenna is not going to make the difference there, as it may in some spots, isolated, stationary. Of course, sometimes not even that, because this is a dynamic obstructed environment we are in. Things are moving around us even though we're standing still. So the pathways of the communication changes from time to time, frequently. So, I mean, we know this in analog communication. We get flutter or picket fencing, we call it. In digital communication with voice, we get pixelations. In video, the same type of thing. So how then is it fixed? Well, let's define it a little bit further. And again, I've done this on some of my videos, but I'm trying to bring it all together here, again, referencing some other technologies, which I will shortly. To reiterate, briefly, if I can, from one of my other videos, what we have when we're communicating in this obstructed world, we have an average signal. There is a minimum signal that is necessary, actually signal to noise ratio, get to that a little bit later, a minimum signal that's necessary in order to have communication. So, a discernible communication. So as we're moving around from spot to spot with the various obstructions, or even in a stationary position with the various obstructions moving around us and between us and the transmitting or receiving antenna, as it were, the fluctuations in signal that occur are not just a few dB, but instead are much more significant. And I talked about their 20 to 30 dB drops, for example. This is where the whole 15 dB fade margin that's calculated in for 95% reliability in commercial or government communications comes in. 15 dB fade margin, not 3 dB, 15 dB. So as I explained in the other video, that what occurs here is that we have what is called constructive and destructive interference. And at the end of the day, something I more refer to as the positive summation and the cancellation, but it's really saying the same kind of thing. So you have some obstruction. Here you are, and the signal that goes the direct point A to point B, line of sight, as it were, if it were, is not the main signal, or not the signal at all that you're utilizing. You get reflected signals that come to you, and I've talked before about how I described how you have the one wave, and then you have the other wave, and in fact, at just the right point, if these are 180 degrees out of phase, they cancel each other out. That's destructive interference, that's cancellation. And you can actually have total cancellation. You can be more than 20 to 30 dB drop in your signal at that point. But then again, you're moving around, so it goes in and out, and that causes your flutter in analog communication. And we've all seen it on FM broadcast radio, two-way radio communications, VHF, UHF. We all know about it. Frankly, we've known about it for a long time, and we even know that you don't have to even go multiple wavelengths further in order to get the signal back. AM broadcast. I mean, you know, it's just amazing how there's so much in front of you. The answers are already there if we really pay attention. If we really watch and listen and recognize. I think in the one video I talked about, and I know in the one video I talked about how as time went along and there was discussions about how to fix this with circuitry, again, receive diversity, transmit diversity, MIMO communications, how to solve this, how far away would you have to move in order to change those pathways to get the signal back? Or if you had a second antenna, how far away would it need to be? And there were discussions about 30 wavelengths, 8 wavelengths. You know, AM broadcast radio 50 years ago, more than that. You know, you're driving along in your car in the highway, and you not only have cancellation, you get distortion, you know, of your AM broadcast signal in your car. How far do you have to go before the signal comes back in again? As a typical example. Miles? No. 250 feet? Something on that order? Yeah. Well, those towers out there that don't have any antennas on the top, frequently, that is the antenna. That is the AM broadcast antenna. Sometimes you'll see them in a line because they phase them in order to cause directivity in the signal and change the directivity in the signal from one time of day to the other to not create interference, whether daytime, nighttime, with other transmitters in other cities. But the point is, the entire tower is the antenna, a quarter wave antenna. Simple. So it may be about 250 feet high. Well, it makes sense, because if you have 984 divided by, say, 1,000 kilohertz or 1 megahertz, you know, and that's approximately 1,000 feet equals 1 wavelength, and 1/4 of 1,000 feet is 250 feet. So there's your 250 feet. But it was in fact 250 feet that you needed to move with your car in order to get the AM signal back again. So you really only needed to go about 1/4 wavelength. The same thing applies. Oh, there are specifics to all of this, but the same kind of thing applies. So when there were, and let's start talking now about the other direction, the other approach that was used to fixing this problem. So the solution that I looked at was correcting this problem of the intermittent significant drop-offs, so that instead we had something more on the order of this, was with the antenna itself. And as it explains in the other videos, in the electric field, there were two main problems. The one being the cancellation kind of thing we just talked about. And there, if you note, we are talking about the same polarization. It could also apply horizontal to horizontal, but the point is, we're talking about if the signal is bad in this area, 1/5 of a wavelength or so away, the signal is good. Let me make a quick comment. All right, I'm going to talk about the circuitry solutions. Again, the receive diversity, full diversity, MIMO type solutions separately. This is an antenna single feed solution. These are synergistic technologies. Oftentimes, there are those that talk about, well, the new technology, how long is that going to last? Something will replace it. You know, there are certain technologies, there are certain sciences, most certainly, and even technologies based on the science that are essentially good forever. They don't outlive in and of themselves and synergistic with other technologies. So I just wanted to get that out of the way. So, and then the other thing I talked about was that in all the obstructions that occur, that there can be flip-flops of the polarization. And if you can capture the various polarizations, that will also benefit you in stabilizing the signal and again helping that 95% reliability problem. So I talked about analog, I talked about digital. You know, how do we show this kind of a thing? You know, when we're talking about line-of-sight communication, we're looking at gain. Of course, that can be measured on a range. It can be measured in an anechoic chamber. These are the types of tools that we have to measure this kind of thing. In the real-world environment, then, with these kind of changes and the improvements that we attempt to make and do make, how can that be validated? How can that be shown? Drive studies are done. For example, many sites are tested. This is one way of doing it. And it can be doing it by hand recording. It can be done by equipment that's available. The Wiltec Blue Rose Analyzer, for example, with certain types of communications. There are methodologies that we have. Because what we're really looking for, you know, say in analog communication, we can't go by signal alone. We go a little bit further. We know signal to noise ratio is really where it's at. But we go further than that, and we begin to realize that there's flutter that's occurring. In digital communication, we have signal, we have fast change, slow change. We have the signal to noise ratio, the same thing. Then we have bit error rate. See, the further you go in these analyses, specific measurements, the closer you get to the real world answer. And in fact, a paper was published separately that really emphasized that if you want to know in your handheld or mobile two-way radio communication, emergency communication, that the real answer is not at all in these things. the signal to noise ratio. Yes, the bit error rate gets closer, but it's DAQ. The digital audio quality in the real world experience. So bit error rate helps you to some degree with that. So bit error rate can help you with that, and by the way, this applies to both voice digital communication as well as video digital communication, IP protocol and whatnot. Of course it can, but and in fact we can do the calculations with the speed of light at 186,000 miles per second, and we see various paths occurring here, and we have a mobile environment, and we can do some approximate calculations to show that in fact as the signal arrives at a different time, we are going to have some bit error rate because the one path is here and the other path is delayed here, right? So, but bit error rate even doesn't do it for us. Signal doesn't do it. Signal to noise ratio doesn't give us a full answer. Bit error rate doesn't give us a full answer. Frame error rate comes much closer, because sometimes we can have some bit error rate, but there's still enough of a frame of the bits that the communication through correction particularly can still be adequate. So frame error rate gets us closer, but it still isn't the final answer. We find then also as the frame error rate increases, as this problem increases, we start getting retries. With greater retries, we get decrease in the throughput. Finally, we get a drop off in the signal completely. Nowhere near 95% reliability. And in fact, when we talk about IP communications, and I apologize here because I'm trying to get a lot of information into one video and some additional information that wasn't in the prior videos. So if I struggle a bit, apologize for that, but I hope this is helpful. So there we talk about like 4 nines or 5 nines, 99.99% or 99.999% reliability, not like the 95% reliability in voice communications. But it all applies. So here we go. Now this is really important. While I was working on the single feed antenna solution, what were others doing? Again, what others were doing were working on the circuitry. Receive diversity, full diversity, transmit, receive diversity, MIMO, these kind of things. They knew they were working with this focus by others was to correct the problem, recognized increasingly as the type of problem that I discussed. So what was known, for example, was when you had Wi-Fi. You had a laptop, and you were attempting to work the Wi-Fi network, whether at home or in a hotel or whatever the case may be, and you didn't have signal. You would move the laptop over a bit, and you'd get signal, and this kind of thing. So the wireless routers, and this works both in transmit as well as receive pathways. We saw wireless routers originally with one antenna, and then we saw that there were aftermarket antennas that are much longer with greater gain in order to try to help the situation, and as was recognized, it helped a little, but based on the discussion before, not as much as would be desired. So then you saw routers coming out with receive diversity, where the one would transmit and receive and the other one would only receive, and they would switch occasionally. If this was not receiving well, this antenna, then it would switch over to this antenna and receive there. So this is what was done, and by the way, the gain of the antenna was not advertised. No, it was the same dipole as on the original one, but the performance was much better. It was described that the performance was much better, but the gain wasn't talked about because it was still a rubber duck. 2 dB or less gain, 2 dBi or less gain. The power was in the diversity. That said, of course, a certain amount of gain
is necessary in order to establish the calculated and real communication over a certain amount of distance with a certain amount of power and receive sensitivity and whatnot. But once that was established, the greater performance improvement by far was in the diversity. Then as time went along, we saw that this went from receive diversity to full diversity with transmit and receive from both antennas, switching back and forth, and this kind of thing. Then further development went to MIMO, multiple in, multiple out, 2 or more antennas. So with further development, we saw MIMO, multiple in, multiple out. Instead of switching either receive or full transmit receive back and forth, the concept that was developed was transmitting and receiving at the same time from 2 or more antennas. Well, this was divided, these are the basics, into 3 basic types: the space-time coding, the spatial multiplexing, and the beamforming or phasing type of situation. The space-time coding was where the 2 antennas would transmit the same information, and this worked very well in terms of increasing the performance in the obstructed environment and increasing the reliable range in the obstructed environment. Spatial multiplexing is different in that a fast, large stream was broken up into segments, transmitted separately. These segments by the different antennas really increased the throughput, but specifically in high signal environments. Beamforming entirely different. Beamforming 2 or more antennas where phasing switching occurs between the antennas, so that if the better directivity of the signal was such that it would be in this direction, the phasing was done such that there would be directivity this way, this way, this way, as it were. Okay, so the question is, did you believe it? How do you believe it? The gain of the antennas were, again, very little. The gain of the antenna was not advertised. It wasn't promoted. The power was not in the gain of the antenna, yet the performance was higher. Similar language, but an entirely different approach. Did you believe it? Well, how do you believe it? You go into the real world environment, you test it many times and that kind of thing. Is there anything better that can be done? We have anechoic chambers. Well, that's not going to do you any good here, but as I alluded to before, Lindgren developed the reverberating chamber. You take the chamber with the absorption panels, yes, but then you put in obstructions, you move these obstructions around in an attempt to document the performance of the MIMO or switching diversity product in the real world. And by the way, the switching and even the MIMO is sometimes done with multiple antennas at different polarizations, so we have both the spatial diversity, polarization diversity, MIMO, spatial and polarization diversity. And this isn't just for Wi-Fi, by the way. This is also for cell phone communication, especially in urban environments. The antennas on the side of the buildings or on the shorter towers, cross polarization is utilized there in the highly obstructed environment for all the same reasons we talked about before. So yes, the reverberating chamber then can help document the actual improvement from these kind of technologies. So again, in the obstructed environment, if you want that intermittent maximum range communication, then it is often entirely about gain, not the switching diversity, not the multipolarized antenna, not the MIMO, that kind of thing. But again, that's going to be intermittent when it becomes a line of sight or a near line of sight communication. Intermittent. If instead you want to increase your reliable range, again, it's range, but it's reliable range, then incorporating the three-dimensional antenna, multipolarized, the switching diversity, the MIMO kind of, these technologies Separately or together, that increases your range, but it's the reliable range. That's the key. This brings us to the latest finally, and that's the COMPACtenna. The magnetic field enhanced antenna. I'm going to refer to existing literature for a moment, an IEEE article that was written to show you something that was done, and then something entirely different. Although from a distance it may look similar, and I'll explain shortly the great distinction. We can have a quarter wave antenna, for example, and it has the performance that it has. For example, with a quarter wave ground plane below it, roughly 0.7 dBi. Yes. All familiar with that. So it was shown that a further development of increasing the wide-banded characteristic of a quarter wave, we've known for a long time that one can create a panel of sorts, a sheet, and increase the broad-banded characteristics. The sheet can be in different types of shapes. And in this article, it talked about if we had a very extended piece, well then, of sheet metal, well then we, foil, we increase the broad-banded characteristic even further. Unfortunately, it starts taking up a lot of space. So, the concept and the test of the concept was taking it and wrapping it, and is referred to by some as the jelly roll antenna. Note here that this is about 1/4 wave, and this is about 1/4 wave. At the end of the day, when rolled, though, it takes up less space. And it still maintained quite some wideband, broadband characteristics. And that's good. So one may look at this pattern that you'll see a photo of here and say, oh, looks a little similar, but it's entirely distinct. At the same frequency, this antenna would be approximately 1/4 wave, but this antenna, the COMPACtenna, is a fraction of that. It's 10% to 25% of the quarter wave. Extremely short. Also, this talked about the wideband characteristics, and that's it. No discussion about magnetic field, performance, the characteristics of the magnetic field, the performance. No, it wasn't about that. It was about wideband characteristics, and again, this is a fraction of the height. So we have approximately 1/4 wavelength here, a little bit less, but a very small fraction of that there. The antenna still has broadband characteristics, in fact, multiple magnetic field resonators, as I refer to it, can be incorporated in the same antenna. For example, the COMPACtenna you see a photo of is for 2 meters, 220, and 440. This is one particular application. Works extremely well and very popular. So, so one might say, well, what about this magnetic field, and what about the electric field, and what about the gain? Let's finish by talking about these 3 key characteristics. Again, the quarter wave antenna with a quarter wave ground plane, as such, we talk about 0.7 dB over isotrope. All right, the theoretical isotrope. All right, let's talk about this. What about if the quarter wave antenna is on a large sheet of metal? What do I mean by large? Let's say we're 2 wavelengths in radius or thereof. What then is the gain? Well, the pattern changes somewhat, of course, and the gain increases. If you simply take a quarter wave UHF antenna, say 450 roughly megahertz, and mount it in the center of the roof of a vehicle, you will get as much as approximately 4.5 dBi gain. With a Wi-Fi antenna at higher frequencies, 2.4 to 2.4835 gigahertz, the gain can be as high as 5 to 6, on the order of 5 to 6 dBi gain, due to the ground plane counterpoise expanse and multiples of a wavelength. This is often not appreciated. At VHF, a little bit less than that, and of course it depends on the shape and size of the panel or sheet metal of the car. So now let's talk about this COMPACtenna. Let's talk about the electric field and then finally the magnetic field. All right, we have approximately a quarter wavelength here. We think in terms of the electric field being of this sort, but then of course it's rolled, it's spiraled. So we can see that the gain then with a large counterpoise, ground plane counterpoise below it, would be indeed substantially vertically polarized anyway, as opposed to an immediate thought of horizontal polarization. And then we would think, though, of course, that it wouldn't have much gain, and we would also think in terms of the impedance mismatch and all of that, with the close proximity of the hot voltage point here to the ground. But then recognizing there are magnetic fields and essentially LC circuitry built in, matching type of circuit based on the specifics of how it is built, the windings, the spacings, and whatnot. And we say, well, still, you know, the gain will be diminished in the vertical polarization in the electric field from a quarter wave, and the answer is yes. Yes. Measured in the anechoic chamber or on the line of sight range, absolutely. But we have the ground plane enhancement with this technology as well as standard quarter waves or whatnot, right? So therefore, the data sheet lists 3 dBi nominal. This is an antenna that performs at VHF 220 megahertz and UHF. It's a conglomeration of that. That is where it comes from. Okay, so we're going to talk about the magnetic field now. As I alluded to in prior videos, this is key in increasing the reliable range when we are, in this particular case, dealing with the substantial utilization of the magnetic field in terms of capture in the first place, but then in terms of the capture at the proper polarization. So, I need to explain first something about the magnetic field, and the near field and the far field. We are dealing with the far field here. Certainly there are near field, magnetic field inductance type of technologies that are being developed for battery charging, for instance, these kind of things. But this is the magnetic field in the far field. 50% of the energy is in the magnetic field. Poorly utilized up until now, and now not only utilized in strength, but utilized in proper polarization, as I explained. So what is the far field? Just to get this out of the way, if you have an example, here you have a dipole antenna, for example, here you have collinear dipoles. The far field is defined by one equation by 2d squared over the wavelength, d being the greatest distance expanse of the antenna. So in the case here, for example, of a collinear antenna, let's take it 500 megahertz, 985 divided by 500, approximately 2 feet in wavelength. So, and we have a 6-foot span here, so we have 2d squared, 2 times 6 squared divided by 2, the approximate wavelength, cancel out the 2, we have 36 feet. So at 36 feet, the far field, you could start measuring this antenna properly in the far field, for its gain characteristics in the collinear fashion. Similarly, we have when you have two sources spaced apart, let's say again at the same frequency, 6 foot, and this applies both in terms of radio waves, electromagnetism, sound, these kind of things. Here we have interaction that occurs, and we have the near field, which is a blend of the electric and magnetic fields. Then we have the midfield, and then we have the far field. What do we have here? Well, what we have is a number of peaks of the performance based on the addition and cancellation in between. It's defined by 2n plus 1 in this hemisphere, 2n plus 1, n being the number of wavelength spacing. In this case, 6 feet divided by 2 is 3, so 2n plus 1 is 7. So we have 7 projectiles, beam patterns coming off of this. Okay then, so with the COMPACtenna, we have a very short antenna, very short. Yet we have reasonable, vertically polarized electric field gain with a substantial ground plane counterpoise. We also have, surprisingly, not really surprisingly, we have wide band performance characteristics and the ability to keep an antenna very small with multi-band characteristics as well. And then we have the magnetic field, and this is key. It isn't and then we have the magnetic field. In the development, in the vision of this, that actually came very much quickly together. Because again, the direction was increasing, the range, the reliable range, the magnetic field. I talked about this, I'm going to summarize again. We have a tower here, we have obstructions, we have the vehicle, we have the tower over here. Vertically polarized, we talked about with obstructions. The vertically polarized electric field can change from vertical to horizontal. This antenna does very, very poorly. An antenna that's vertically polarized and capturing the signal. Okay, what about the magnetic field? I talked about when the polarization of the electric field changes, so does the magnetic field. So, the polarization of the magnetic field changes as well. Let's address that. But first we need to address what is the utilization, the ability to utilize the magnetic field. Well, when you have two vertically polarized stick-style, mast-style antennas with their electric field and then their magnetic field, these magnetic fields do not couple well. Just as with transformers, certainly you could create a transformer with two wires juxtaposed, parallel. It doesn't work very well. The transformers, as we know, are built in this way with coils, or in this way with an inner and an outer type of coil. Similarly here, we have, again, we talked about the electric field before, substantially vertically polarized. Here we have magnetic fields, different portions, different frequencies of this spiraled foil. So, we have a vertically polarized electric field, and we have a vertically polarized magnetic fields. Distinctly different. This is good, because when this electric field switches from vertical to horizontal and is not very well utilized, and the magnetic field switches from horizontal to vertical, not only is it not captured well by this style of antenna, but it's in the wrong polarization. Even if you had an antenna that was able to utilize the magnetic field well, if it's in the wrong polarization, that's not good. But guess what? When this vertically polarized signal switches to horizontal and the magnetic field from horizontal to vertical, voila, this captures it. So therefore, in your obstructed environment, as you potentially lose a substantial amount of the electric field, you are capturing some utilizable, a magnetic field. So you are increasing your reliable range. I hope that you enjoyed this video, that you got something substantially out of it. Normally, I like to present or speak in a slower fashion, but wanted to get a good amount of information in this video by request from multiple sources, from conversations that have been had. I hope this is a reasonable attempt for all of you in getting all of your requests in this single video. Now you have an antenna, in summary, that's very short, wideband, multi-band, substantially good vertically polarized electric field gain, and the ability to increase the reliable range with the magnetic field, substantial utilization based on its construct, based on its magnetic field, and based on the polarization of its magnetic field relative to the electric field. The proof is in the pudding. It works. And that's great. I have such a passion and a purpose for the conceptual development from the very start. It's great to have a product that meets those physics concepts. Thanks again.